In this first lecture, I want to talk about patterns of resonance, okay? And there's a worksheet that accompanies this. And I want to talk about what I call the first type of a pattern, okay? And there's basically 4 or 5 patterns depending on how you count. And some books might do it a little different depending on what they call the first pattern, the second pattern, but everybody will have these patterns, okay? Now, the first pattern that you have, and you want to print this worksheet out and follow along with what's shown there. So A just stands for any atom, okay? And whenever you have a lone pair next to a pi bond, okay, I'm going to draw these in red here. And in this video, I'm going to use blue for my curved arrows, okay? So when you have a lone pair next to a pi bond, it's possible for that lone pair to be at either of the ends. So here or here. Now, there's a very, let's draw this product here. Okay. And I will draw in the electrons. So these 2 electrons that used to be a lone pair are now in that bond. You could even draw the 2 dots on that line. And these 2 electrons from the bond are now on A. All right. Now, if we follow the use of the formal charge, remember how the foot of the arrow becomes positive and the head of the arrow becomes negative. Now, the probably don't want to do that in red. Let's use yellow for that. So remember, the one in the middle is not changing because the electrons are flowing towards A and then flowing away from the central atom, okay? Now, it looks like, if we just look at the bond, it looks like the bond is changing from the right to the left. Do not, please do not show the movement of electrons like this, okay? That's not correct, okay? And the reason why is because atom A has 2 electrons already, and then you're pushing more electrons onto it from that, you know, from that bond. So you're probably going to exceed the octet. You're just having too many electrons. So the electrons are going to flow towards this sp2 hybridized atom A on the right. Let's look at some examples, okay? So this is the pattern. This is the pattern we want to look for. A lone pair next to a pi bond. All right. This is an ester functional group. Esters are important, and the reactivity is dictated a little bit by the resonance stabilization that they enjoy. So we can take these 2 electrons, which is a lone pair, and these 2 electrons, which are a pi bond, and move them around a little bit. Didn't I just say I was going to use blue for the curved arrows? Okay. All right, so there I've attempted to draw some curved arrows. Now let's draw, so we're just drawing a bond line structure here for all the carbons, which aren't really needed or necessary. So let's go ahead and draw this all in. And I'm going kind of crazy here with the colors. I'll probably stop this after a while, but I just wanted to show you how the electrons are conserved here in this system. The lone pairs are now making this pi bond, so here are the 2 dots, right? And the electrons that used to be in that pi bond are now up here. Now let's switch back to yellow to identify formal charges. The foot of the arrow becomes positive and the very head of the arrow becomes negative. The one in the middle doesn't change, okay? So that would be a great way to show the curved arrows in blue, and then the final structure here with plus and minus. You don't need to really worry about putting all those dots in red and color coding things, okay? Let's look at example number 2. Example number 2 is a structure known as ozone. The very sole reason that ozone is somewhat stable is that it's resonance stabilized. So let's draw the Lewis structure here for ozone. It's a crazy structure. You've got some formal charges in it. Now it's a neutral molecule because the sum of the formal charges is 0. So this is O3, ozone. And let's draw the curved arrows, in blue. And I'm going to not lasso things, just to be easier on you for taking notes. Okay. And we'll draw our resonance arrow. Remember, this means equivalent or nearly so. And, So let's go ahead and draw in what we have here. So that's what the curved arrows is telling me. I'm now going to have a double bond on the left and a single bond on the right. And let's draw the formal charges, okay? So the foot of the arrow becomes more positive, so it becomes a formal charge of 0, and that makes sense because it has 2 bonds. The oxygen on the very right is going to become more negative because the arrow is pointing to that oxygen, and that makes sense. Oxygen with 1 bond is negative. And the oxygen atom in the middle did not change in formal charge. It still has 3 bonds and 1 lone pair, so that's a formal charge of +1. Okay. So let's do some more examples. Example 3. Okay. And if you're, understanding this and you feel fine with this, skip ahead in the video by all means. So let's talk about the azide ion. Sodium azide is located in your car airbags, and it's a shock sensitive, or it's an electrically activated explosive that detonates. Hopefully you never have to experience a car crash and an airbag going off on your face, but so I'm trying to show you a variety of things here, different types of atoms, different types of bonds, and so on. And this is one of those rare instances where you have a -2 formal charge. And so let's see, in blue I said, we will draw the, so here's the lone pair, right? And here's the pi bond. A triple bond is a pi bond, right? So we can draw this kind of hot potato motion across the molecule. And what are we going to get? We're going to get a nitrogen now that has a double bond, and the triple bond changes to a double bond, okay? And what about the formal charges? The foot of the arrow becomes plus, the head of the arrow becomes negative, and the middle nitrogen is still, still formal charge of plus. And so we can just add those electrons in. Okay? So remember again, the movement of the curved arrow is always 2 electrons. Let's look at an example 4. So now we're looking at, somewhat larger organic molecules. And this is called a carbanion. It's allylic. There's a lot of names for such a thing, but basically when you have 3 carbons attached to a negative charge, to a carbon, it has a formal charge of -1. And we'll talk about what that's, the name of that later. So just remember that that's a -1 formal charge. Something like this has a formal charge of +1. Okay, there are no lone pairs on carbon. So we're dealing with this guy right here, right now. And you can definitely see, let me highlight those electrons in blue. You can definitely see a lone pair next to a pi bond. Now again, please do not show this movement of arrows. That's wrong, okay? That's wrong. If we did that, how many electrons would carbon have? It would have more than 8, and we don't want to do that. So undo, undo, undo. My bad, right? So what you want to do is take the lone pair, start with the negative, okay? If you ever have a negative charge, start with that atom. We want to move electrons going this way, away from the negative. Let's draw a resonance arrow, and let's draw in all these H's and C's and stuff. Only the lone pairs and pi bonds move in a resonance situation, and so you're going to have a double bond on the right, a single bond on the left. The 2 electrons are going to move to this over here, carbon over here, and as I mentioned, here's the box still. A carbon with 3 bonds and a lone pair is -1. All right. So take a look at your worksheet there. Actually, let me give you one more example because I just want to show you tandem moves. Tandem moves. Okay. Let's say I have a molecule like this. And this is kind of where the spork analogy of resonance breaks down. This is like a Swiss Army knife with the tweezers and all these little gadgets in there. So start off slow and don't try to show too many curved arrows at once. We've got a lone pair, we've got a pi bond. So just take it one step at a time. Boom, boom. Draw your resonance arrow there and draw a new structure that you produce. So this is how we generate and draw additional resonance structures. Only the lone pairs and pi bonds move. And let's see where that pi bond went. All right. The lone pair becomes a carbon-carbon pi bond between the 2 very-most left carbons, and the lone pair ends up here. Now what you can do is recognize that there's a lone pair adjacent to an additional pi bond. So you can rinse and repeat, so to speak, and you can do this one more time, okay? So when we get to the second semester organic chemistry, we will learn about phenoxide, this molecule here, and it has a total of 5 resonance structures. And the reason why is because you have a lone pair next to a pi bond, which becomes another lone pair next to another pi bond, which becomes another lone pair next to another pi bond, and there's just so many different resonance structures there, okay? So, yeah. All right. So, now work on your worksheet. And if you're watching the video and you're not in my class, I will just list out what those molecules are. They're this one here. Okay, I'm not going to write the answers here in this YouTube video, so please just work on it yourself. Check with a tutor or an instructor. So, you know, there's one more resonance structure you can draw for that one. There's one additional resonance structure you can draw for this one. Try to work on that. See what you come up with. This molecule here is called the guanidinium ion. It's derived from guanidine. It's used as a component in some biological buffers, I believe. And now this one has 2 different resonance structures. So you'll have, answer number 1, and then you'll have answer number 2. Now, using the curved arrows is part of the answer, so please show your curved arrows, okay? It's very important. The curved arrows are more important than drawing the correct formal charges and bonding in those guys. Your last molecule, I believe, yes, is this guy here. I'm having a hard time drawing these in here. Let me draw all the C's. It's probably best as a beginning organic student to have all of the carbons drawn out instead of a line drawing. If you're comfortable with line drawings, that's great, but sometimes it's a little bit difficult to identify where there are electrons and where there are pi bonds, so I'm going to help you out by drawing a full Lewis structure here, and that's a formal charge of minus on that carbon, and there's a double bond, so there's 2 hydrogens here. Okay, so that also here on this problem D is going to have 2 additional resonance structures. Okay, thanks for watching.